What is transmission line? To understand this concept, let's say we have a pair of wires close to each other like this. If I asked you to apply a DC voltage source and find out the current going through these wires, you would say it is zero because these lines are open circuited, right? So the impedance looking is infinite. How about if we apply an AC signal though? If we apply 1 kilohertz AC signal, what is the current? You would still say it is open circuit, so infinite impedance, zero current. What about 1 megahertz? Yes, still open circuit, so zero current. What if we apply 1 gigahertz, 10 gigahertz, or even higher frequencies? Does it still look open circuit to you? Well, visibly yes, but actually there is some current that will flow through these wires, and that current is actually because of the parasitic capacitance between these two wires. So it turns out at higher frequencies there is some current flow through these wires. That means the higher the frequencies, the more the current should flow, right? So at very high frequency, let's say 1 terahertz, this should effectively short circuit this line because this will have very small reactance, right? So infinite current should flow at very high frequencies. That is not true because these wires also have some self-inductances. So you can replace these two wires with an equivalent circuit like this one. So at higher frequencies, a current is flowing through these wires even though they may look open circuit to you. So that means this pair of wires have certain impedance. So no longer are these two just a pair of wires, but rather the transmission lines. And together with these L's and C's, they form a certain impedance, which we call as characteristic impedance. Now, what determines the current flowing through these wires, or what determines their characteristic impedance? Well, these L's and C's, they do. For example, if you increase the value of this capacitor, the reactance goes down and the current increases, which means the characteristic impedance of this line decreased. Similarly, if you increase the inductors, their reactance increases, which means the current reduced and which means the characteristic impedance increase. This is what is told to us by this expression, which states that the characteristic impedance of transmission line equals square root L by C. To understand this expression, let's take an example of microstrip transmission line, where we can assume that the ground plane is ideal because this metal is very wide and continuous. So if it is ideal ground plane, that means we can ignore the self-inductances of the bottom bar. So this microstrip transmission line can be reduced to this equivalent circuit where these inductors are coming from the top metal and these capacitance are from top metal to this metal. Okay. So what do we mean by Z0 equal to square root of L by C? Does it mean this section? Does it mean if I size my L and C's according to this formula, it will give me Z0 impedance? If that is the case, I can replace this section with this Z0 and all of those sections with the Z0, and that it means all of them are in series. So then they should add up, right? So if I keep on adding these sections in series, it will become infinite impedance, right? That's not true. Transmission line is providing us Z0 impedance, which is not infinite. So if it is not in series, maybe this section means Z0 impedance in parallel. So we can replace all those sections with parallel Z0. If that is the case, they are all in parallel. So they should give us zero impedance, right? But now that is again not the case. We are supposed to see Z0 impedance. So this is one difference between characteristic impedance and a normal impedance. A normal impedance would add up in series or would go down in parallel. But a transmission line is a special kind of impedance that does not add up in series. In fact, if you keep on stacking or adding these lines, it will remain Z0. That is why we call it as a characteristic impedance. To understand this thing more in detail, let's take a numerical example. But before that, I should mention that this expression is only valid when you are analyzing a very small piece of line. For example, if you have this transmission line, and if you analyze this very small section where the length of this section approaches to 0, then you come up with this expression. Okay, let's say we want to make a transmission line with characteristic impedance 50 ohms. Okay, so with that formula we come up with this expression. Let's say we choose C equal 100 femtofarad, and it gives us L 250 picohenry. Let's say we put together some sections, some of those L and C section, and terminate that line with 50 ohms, and let's try to see the impedance looking at this point. Let's see what happens. So this is Smith chart. Right now we are at the center. Looking from here, we have 50 ohms. Okay, we add this inductor, we move to this point 2, then we add this capacitor, we come down to this point 3, then we add this inductor, we move back to that point, then we add this capacitor, we come back down here again. So you see we keep on moving up and down on this contour as we're moving this transmission line. And at the final end, when you add this inductor, you come up at this point again, which is 50 ohm. So you see what is happening? It's not adding impedance, it's not subtracting impedance. Instead, it's moving on this contour constantly as you're moving on transmission line. So if you terminate this line with the same impedance that was the characteristic impedance of this transmission line, you end up seeing the same impedance, which is 50 ohms, right? Well, I'll be honest with you. If you go and simulate the circuit, you will not see 50 ohms. Instead, you will see 54 ohms at 5 gigahertz. So why did that happen? Well, this has to do with the fact, as I told you, that this expression is only true for a very small transmission line, for a very small piece of line, which means for that very small piece of line, this L's and C's will have very small value. But here I arbitrarily choose C 100 femtofarad, right, and came up with L, which was also higher. So let's choose C with 1 femtofarad. Then it gives L 2.5 picohenry. Now if you put those values here and simulate this circuit, you would see you're very close to 50 ohm. Or better yet, let's put 0.1 femtofarad. It will give 0.25 picohenry. And now you will see you are exactly at 50 ohms. This line will exactly give you 50 ohms. So this is truly a 50 ohm characteristic impedance. Okay. Now, so what's happening? So you see, when we had bigger values of L and C, we're moving on this bigger contour, like this, back and forth. As we're reducing the values of L's and C's, we are moving in this direction. So when you analyze this piece of section, which is very small, you have very small values of L's and C's. Essentially, you are just moving on this dot. You're not moving up, you're not moving down, you're just staying on this dot. So looking at every point, 1, 2, 3, 4, 5, 6, you will see the same impedance, right? Which is what a transmission line is. Now, one more thing. Here I mentioned 5 gigahertz, but here I am saying infinite bandwidth. This is another interesting property. So an ideal transmission line is frequency independent, which means if you synthesize L and C's according to that formula, Z0 equals to square root L by C, it is frequency independent. No matter at what frequency do you check, you will get 50 ohm impedance as long as you terminate that line with the 50 ohm load. But here, these values were bigger, and it will give you different impedance at different frequency. For example, at 5 gigahertz, you will see roughly 54 ohm resistance. So why did that happen? This has to do with the fact that this is not a transmission line. This was an approximation. And that is why you should also see I have this start and end inductor 125 picohenry. They are not 250 picohenry. Because this is very small piece of line, and this is not actually transmission line, this is lumped equivalent. So I had to add these sections to make it look close to 54 ohms. But here, you don't have to worry about that because you are analyzing an infinitesimal small line. These inductors or capacitors are infinitesimal. So no matter what inductor or capacitor you put here, or no matter if you start from a capacitor first or inductor first, it will always give you a 50 ohm. Okay. So now that is why when we have a transmission line terminated with the matched load, no matter at which point you will see the same impedance of 50 ohms. And at any frequency, infinite bandwidth, it's frequency independent. Okay. But wait, the transmission line that you design are not infinite bandwidth, right? Why is that? Well, this has to do with this fact that we have been saying z not equal to square root of L by C, which is not true actually, because it is R plus j omega L divided by G plus j omega C, where R is the resistance of that wire, loss of that wire or metal, and G is the loss through that dielectric. Okay, so you can see this expression has a frequency factor. So this impedance is frequency dependent, right? More reason, if you ask, for example, if we consider a microstrip transmission line where we don't have a same dielectric for these two metals, we have air above this metal and some dielectric, so then we have to approximate this dielectric with an equivalent E, right? And you will see this will become frequency independent. That will change your L's and C's based on your frequency, which will change your characteristic impedance. You can also see that this metal has some resistance, and this resistance typically increases with the inductor because of the skin effect, right? So at different frequencies you will see different resistances, which will again change your loss and the characteristic impedance of the transmission line. So that is the reason the transmission lines that we design in practical are not infinite bandwidth. But yeah, given that you can remove this and remove this, and if you can just synthesize with this L's and C's, which do not change with respect to frequency, you will end up getting an infinite bandwidth transmission line. Okay, so now we have seen what are the transmission line. Let's try to understand when, why, and where do we use the transmission line. So let's say we have this transmission line terminated with this 50 ohms. If I excite it with a frequency which is very high, which means the wavelength is very small, so you'll see that the voltage on this line at each point is different because the wavelength was very small, right? Compare this case with a very high, very small frequency. Let's say we have 1 kilohertz where the wavelength is very high. That means on this line you will only have this much part of that wave, right? So you have approximately same voltage of that line, right? So you don't see those effects of transmission line as much here as much as you will see here, right? So the rule of thumb here is when the dimensions of your components are comparable to the wavelength of your input signal, then you start thinking about the transmission line effect. So normally people will come up with this rule of thumb. They would say, okay, if this length here is lambda by 20 or lambda by 10, this is a transmission line, right? So you may have heard I keep on saying at high frequencies current starts flowing through these wires because of this parasitic capacitance between the wire, high frequency. And that means the transmission line concept does not exist at lower frequency. This is not true. In lower frequency we have very few examples of the wires which are that long that will cover this entire wave. For example, if this line was this much long and it covers your entire wavelength, so even at this lower frequency, the 1 kilohertz which I said, it will behave as a transmission line, right? So this is the thing that we should keep in mind. At higher frequencies, the dimensions are comparable to the wavelength. That's why they behave as a transmission line. But at lower frequencies, no, those wavelengths are very big, so they're not comparable. So you can just consider this thing as just one node, which you do in your circuit analysis. Okay, this is one node. So you assume there is the same voltage here. But that is not true for the higher frequencies, millimeter waves. Okay. So this is when we use the transmission lines. Okay. Now Why do we use transmission line? Well, first off, we can't avoid them. At high frequencies, they behave as a transmission line, so we have to start thinking about them. Secondly, because of the beautiful, beautiful properties that they have. For example, if the transmission line is quarter wave long, it can invert your impedance. For example, for some reason you don't have inductors. You can use a capacitor and a quarter wave transmission line, and if you look at the impedance here, it will look inductive. Yeah, and for example, if you have an open circuit at one line, and if it is quarter wave long, it will appear as a short circuit. It changed the whole high impedance to low impedance. Similarly, if you have a short circuit at this line, and this line is lambda by 4 long, it will look like an open circuit. Isn't it amazing? And this half wavelength line. Okay, so up till now I've been telling you that if you have a transmission line of Z0 impedance, and if you want to see the impedance looking into this line as Z0, then you also have to terminate this line with Z0 impedance, right, with the matched impedance, right? But you can get away with this if you don't want to use the same load or same line, if you use half wavelength line. Yes, so it turns out if your line is half wavelength long, no matter what is the characteristic impedance, you end up seeing the same load that you have here. Okay, now where do we use these transmission lines? Well, if you come at millimeter wave domain, these are everywhere. For example, the Wilkinson power divider, you use quarter wave lines there to make a 3 dB splitter. For example, a quadrature coupler, where you want the outputs to be 3 dB splitted in addition to the 90-degree phase shift. You use quarter wave lines and couple them. For example, if you use quarter wave line and short one end, it can behave as an inductor. And if you make it quarter wave long, it can behave as an infinite inductor at that frequency. So it can behave as an RF choke. So you use it for the biasing. If you have quarter wave long, you have this ZL. Looking here, you will see this impedance. So it can transform the impedance. So you can use it for matching. Similarly, if you have a lambda by 2 long line which is open circuited at one end, it can radiate. Yes, it can act as an antenna. So you may have heard of patch antennas. They are lambda by 2 long. They are a transmission line with the open circuit here at this point. You can use them to interconnect, connect one point to another one. Or you can ground this lambda by 2 long line and it will behave as a resonator. So you can synthesize oscillators based on these lines. Okay, so before ending this video, let's talk about a little bit more on this thing, interconnects. So let's say you have two circuits, okay, and you want to connect them. For example, it has some output, it has input. You want to connect that output with this input, right? For example, let's say they have ground. So somehow you come up with a way of ideally grounding them, right? So their grounds are connected ideally, and the signals is just connected following this just one path. Now at lower frequencies, this is okay, right? This is what you do. You just put a jumper wire between these points and then they get connected. So at lower frequencies, this is okay. But this is a disaster at high frequencies. Why? Not only will it have skin effect at higher frequencies, but this will have some inductance. And at very high frequencies, this inductance will become so high, not this inductance, let's say the reactance of this inductance will become so high that this will eventually become open circuit. So nothing will flow across this dimension, right? So at lower frequencies, you were easily just putting jumpers in your breadboard or PCB and connecting stuff together. But at higher frequencies, if you don't take care of those wires or interconnects that you're connecting them, you can end up getting nothing, right? So that is why we have to consider a transmission line. That is why you have to take care of the ground path as well, so that if this thing has some inductance, it also sees that capacitance with this path. In other words, it forms the same LC section that we have been talking about, and it gives us a constant impedance of 50 ohms, right? Or whatever characteristic impedance you are designing it for. So if you design this interface for 50 ohm and this interface also for 50 ohm and connect them with the line of 50 ohms, all of your power should essentially flow to this thing, right? Nothing should get reflected, or you should not see open circuit. So this is why we have to use transmission line. There is no other way, right? You can't just use one single wire to connect this point with that one. Okay, this is all about transmission line and the characteristic impedance. If you have some feedback, if you think there is some conceptual mistake in my understanding, please do let me know. It would be great to hear from you guys. Okay, till next time, bye-bye.